Great. It's really a pleasure to have Nathan Kutz here. He is my counterpart, another director of an NSF-funded AI Institute with the AI Institute for Dynamical Systems. So looking forward to hearing what's going on from you folks at University of Washington.
Thank you so much. Hey, pleasure being here. Great to be in Boston. Thank you, man. Hopefully follow up on that and maybe can contribute to some things that Matt also said as well. A little shift in what the talk is about. So the talk here is just going to be about taking data, and as mentioned, it's really we're at this AI Institute of Dynamic Systems, and so we think a lot about data which is evolving in space and time, and thinking about collecting that and starting to learn models from that. Really starting to think about what kind of architectures or methods you can bring to the table to learn from that data, especially as we're really kind of in this spot where, if you ask me, the star of the show today that we overlook all the time is sensor technologies. All this is powered by data. And so really, if you ask me, it's all about our sensors, and our best sensors sitting right there with you in your pocket, which is your phone. It's amazing what we can collect and how quickly we can collect it and very quickly get, in some sense, maybe even overwhelmed with that data. So what can we do with the data? And so I want to start thinking about where Einstein was in 1916, which is, it's not just about building a model from the data. It's one of the really key aspects is what we're really thinking about is representation of this, both in terms of, let's say, what we might call governing equations, but also in which coordinate system. We have to learn these two things simultaneously if we're going to make great progress. So I'm going to give you a quick example of this, or at least this is one person's opinion, okay? But this is this idea that Einstein had, which is it shouldn't really matter what coordinate system I'm in. The physics that I'm monitoring, it's the same, but I could have potentially a better coordinate system to represent it in. So that's really kind of a key idea. And so here's what the talk's really about. Two pieces. And I generically give this picture, but the idea is I pull in the data from whatever I could measure it with. Okay? So that doesn't make it the right coordinate. Oftentimes we're measuring things now in pixel space. Pixel space is not a good coordinate, right? You get an 8K video feed, pixels are not the right coordinates, but the idea is to map it from what you're seeing into a representation where I can now, in this layer here, have a latent representation, which would give me a way to represent the dynamics in a good way. And then I come back out. So I want to map into it and map back out. So in some sense, I want to try to bring targeted use of neural nets to the table so we can still come out with an interpretable model at the end of the day. So let me give it to you in context of a problem we know and we've studied forever. It is the first physics problem, I think, really. It's the motion of planets. So, right, this is good. Before we could even write things down, we were studying the motion of planets. Humans were known to be trying to observe and try to predict the motion of planets. And so here, what you're seeing is the retrograde motion of Mars, and over here is Saturn. And so one of the oldest questions we ever asked was, how do we describe these planets? So fascinating were these. Like, if we didn't have light pollution and no electricity, at night you could go outside and this is what you're looking at. And the most interesting things to be looking at are these planets because they're like moving around over time. And people were very interested to it. So we gave them names of the Greek or Roman gods, right? And we tracked these for a long time. And then the question is, how do we model it? And the first predictive model of this came out of Alexandria, Egypt, 150 AD. Claudius Ptolemy, and this was based purely on geometry. Geometry had already been around for this point, right? Euclid wrote his Elements in about 300 BC, also out of Alexandria. So this is, like, to me, the most fascinating city of the ancient world in terms of science. And this is sort of the model. The model, of course, is the Earth-centric system, which one way to describe it is we're at the Earth, and the way you describe this planetary motion is circles on circles on circles. Okay, so another way to think about it is if I take this as my data input, what this neural network would be in charge of learning is this coordinate system in which the dynamics here is essentially a Fourier transform now. This is the earliest version of a Fourier transform. Represent motion in terms of some periods with amplitudes. Okay, So this is one perfectly good model of planetary motion. A second model that we came up with much later as we had calculus, we just made a simple coordinate change, right? It wasn't so simple, actually. So if you were the one making that coordinate system, you're gonna be in trouble with certain entities. So here it is, and this is the idea, is I bring this in. Now what I'm trying to learn is a different coordinate system in which I have a heliocentric coordinate system, and in which if I can place it in this coordinate system, here is my representation of the dynamics. F equals ma, so I have where I have this inverse square law. So both are equivalent, right? Just like Einstein would say, I can make that circle on circle model as accurate as I would have this model be. And it's just a matter of which one do I want to be using in practice. Now, one of the things I want to highlight here is I think something very important, even towards Matt's talk previously, which is in the first model, where we fit these ellipses to the data, right? This Earth-centric system where we're circles on circles. This is purely, in some sense, an interpolation model. You fit this, and now that model's constrained to fit the behavior that you see there, and it's very hard to, it's fitting directly to that. Whereas here, once you have this is a big change because now you have this generative model F equals ma, and even though you applied it to this planetary motion, you could do the following exercise, which you kind of always wonder when this actually happened. We don't have a written record. Who was the first person to say, hey, I wonder if we could launch a rocket? Maybe the word rocket didn't even exist at this point. Go up to the moon, land on it, and come back, right? And at some point, when you have this model, you could actually start making calculations about the feasibility of this, right? You take a might of a nation, of many nations competing to do this, and eventually in 1969, you in fact do this. You put somebody on the moon, bring them back, okay? And by the way, it's interesting to watch this history because the first thing you send up is not a human. You send up first like nothing, and then you send pigeons and then monkeys, and you go, okay, actually F equals ma seems to still hold up there, right? Because this is an important thing. We don't know what if the physics changed up there, and we were able to do this. So I want to highlight this because this is ultimately something really important to learn, an extrapolation engine. And there's such a big difference between extrapolation and interpolation. And I think this is a really challenging point. We use the word generalization a lot in machine learning. I hate that word. And I hate that word because sometimes when you're generalizing, you're just interpolating. And that's a lot easier. When you say, oh, it generalizes well and you're interpolating, so of course, you're interpolating. That is a much easier challenge than the extrapolation task that you have. I would love that to be more precise when we talk about generalization in machine learning. Okay, so here's what we're going to go after then in this talk. I've already shown you I can come up with a variety of models, right? So, or coordinates and models that go together, at least two in the planetary motion piece. And then I want to just do this idea here. This is a very simple mathematical architecture. I'm going to go from measurements. And whatever my measurement is, I would like to learn a map to a state representation X, where X has some dynamical evolution. So the things I don't know, I take measurements. I don't know this measurement model to take me to X. In other words, I have to learn the coordinate I'm going to even work with, and then I have to learn the dynamical evolution. So given a set of data, I have to learn H, F, and X. This is a terribly ill-posed problem. Okay? But it's kind of in some sense what we are dealing with in the modern world, collecting data in so many different architectures. And so the question is, what are the options for us? And so I'm going to walk through a few things we can maybe do. So remember, I have the choices to make here. It's my talk. I can do whatever I want, right? But these are just some options that you could go with. One thing I could do is just pick a linear model. Now, why do I like linear models? Because it gets me right back to the human understanding piece is, I'm going to take this, I know it's nonlinear, but I'll try to just approximate it with the linear model. And the reason I like linear models is because this is the only thing I actually ever learned in a physics degree or applied math degree is Oh, it's not, find a way to make it linear, and then write down my exponential solution. Okay, I'm not really lying, right? I tell my students this all the time. It's like, if you know how to differentiate an exponential, in really good shape. Okay, because now you can solve a lot of problems you're gonna have to solve. So I love this because I want to come here and represent this. Now, I've already prefaced, you know, I'm biasing your look here because I'm gonna look at things that are oscillatory in nature. Now, this seems terribly constraining. However, it actually works amazingly well in some problems. I want to tell you one of the methods that can do this directly on data. That is what's called dynamic mode decomposition. So what you're going to do is take snapshots of your system, whatever measurement space you have. And here what I'm going to just do is go ahead and assume that I actually am in the state space, or whatever my measurements are. And I need to learn a new coordinate. I'm just going to take this, and what I'm going to do is just do a regression. And I'm going to do what's called bagging optimize. So to sort of make this with some uncertainty metrics and robustness, I'm going to take subsets, regress to that linear model solution, do this over and over again so I can get mean and variances of the modes and their eigenvalues and their weights. Okay, so this is dynamic mode decomposition. It's just basically take the data and build that linear model. Okay, the nice thing is this sort of developed with various people here. Now it's as easy as this: pip install PyDMD. Now you have this package. This is one of the really amazing things that's happening in today's culture of open source code, is that you can just say, oh, pip install, and you're in business pretty quickly with this. Okay, and so you can do this, and I'm going to show you one example of this, which because you might think, well, this is pretty limited. My model is clearly harder than linear. But then I want to show you this example here. And this is just, again, there's so many examples I could show, but I just want to show you one thing. What you're looking at here is flow around this tire. It's a virtual tire. I was on sabbatical this last year in London, and so I worked a little bit with McLaren Formula One team, and simulations around the tire are important for them. And so this is a day-long simulation, okay? And what we're looking at here is there's 4 planes in which they collect the data, and here's this turbulent wake that's being generated on this thing. This is, this is an LES simulation, so you're approximating major Stokes. It's a fully nonlinear dynamical system, high dimensional, chaotic behavior, turbulence, okay? And I basically say, all right, that's my linear approximation to it. I just do a regression onto this thing. And I think what's kind of remarkable, if you just look at this, it is a remarkable representation. And even this thing is, though it's exceptionally high dimensional, I've now collapsed this down into like 6 degrees of freedom. Okay. Now, you do miss some of the very high frequency features, but you really get a lot of the flow physics right with a linear model. Now, the nice thing here, this is from time, let's say 0 to 3 and some non-dimensional units. This is time 3 to 6. I can now just trivially give you the future state prediction within, I hit return, there it is. It's like a 1 second, where this is a full day of simulation on HPC. So these are the kinds of things a linear model can do for you. And I always like this as the baseline. For me, personally, this is my baseline. I have some data. First thing I do is, how well does a linear model work? It's trivial to do. I mean, really, this is 5 minutes of code to do this. It's not like I'm saying, okay, build this architecture, do all this stuff. It is literally probably out of that 5 minutes, 4.5 of them are you setting up your data matrix. Okay. We can do better even though with a linear model. Notice what I did is I just took the data to try to build a linear model directly. I could instead say, well, what if instead I did one extra step here, is I learned a map, right? So I don't just work with the data you gave me. I try to learn a coordinate change, and I want to learn this coordinate change through it with an autoencoder, so that now I get a better representation of it for our linear dynamics. Okay, so here's the kind of idea of what you get. I take my data directly, I learn a transformation to a new coordinate system, late states, and then I try to learn a new linear model there. The whole idea here is that I'm trying to use it as a linearizing transformation. So maybe your data is quite strongly nonlinear, The linear fit doesn't quite work as well as you want. Well, maybe you just need to warp it into a new coordinate system. Linearizing transformations have been around in physics for quite a while. And so this is kind of the idea of this. All right, so if you do this, you can actually start warping things like even from here. This is a simple example, which is flow around a cylinder. So this is von Karman vortex shedding here. It's actually weakly nonlinear. It's not very strongly nonlinear. So what we did is say, well, let's take this, look in a low dimensional space. So the autoencoder is going to look in a low dimensional space and force it in that low dimensional space to be linear. Then we can collapse this down to a model, which is 3 degrees of freedom linear. And so now we can evolve this in this latent space and linearize this nonlinear dynamics. This was sort of a simpler example because it's weakly nonlinear. You can do much more difficult things. We did what's called Kuramoto-Shibashinsky equation, which is exhibits spatial temporal chaos, and it's not that low dimensional. So we built a little beefier autoencoder structure in here, but again, map it to a new latent space where you enforce linear dynamics. And in doing this, this is with Craig Jin, we were actually able to basically linearize this Kuramoto-Shibashinsky equation. And again, if you look at the history of linearizing transformations, the first and most famous of them was in 1950, Cole and Hoff came up with the Cole-Hoff transform. These were independent works, by the way, for the Berger's equation. We were first starting to study shock waves in the 1950s, right? What would happen as we got close to the sound barrier? So people were investigating this and looking at this nonlinear PD that you could actually linearize. It's a fantastic linearization technique. The next set of linearizations would come not until the early 1970s with what's called the inverse scattering transform, which could linearize just a very small collection of completely integrable partial differential equations. But this is, and then we haven't made much progress since. It's been 50 years. We haven't found anything else that we could actually linearize. What this gives me hope is the machine learning is telling us I found a way to linearize it, which kind of gives me hope that maybe one of you can. I'm not saying me, I'm too old now, but maybe one of you guys can actually come with the breakthrough, because this is actually finding a way to linearize that, which I think is fascinating. So part of it is there's even a storyline here around machine learning tell you, actually I can do this. I found a way. We don't necessarily know how to interpret what it did, but it found a way to kind of do this. And so maybe there's a way for us to actually do the practice. So those are linear models. Let's go to nonlinear models. And so nonlinear models, now we're going to broaden our scope a little bit here. And so for nonlinear model, we'll allow the dynamics to have a nonlinear evolution. But I'm going to come back to this. And so what I really want here is, again, same kind of architecture we had before, but what I'm going to impose here on NatF is going to be important, or at least it's a viewpoint. And we're going to impose parsimony. Whatever representation I have of the dynamics, I'm only going to allow a few terms. Okay, so this goes to Matt's point, right, which was, if you look at Maxwell's equations, right, you can go online right now by this afternoon on Amazon. You have a shirt that says, "And God said Maxwell's equations," right? What we're looking for is relationships among derivatives. This is how, ever since Newton, this is how we advanced with all of our technologies, right, including all of our Wi-Fi and this laser pointer. Right? These are all basically structures which allow us to represent relationships among derivatives. And that's what we're going to go after here, saying, if I believe my physics relationship among derivatives, I'm going to go find it here. But more than that, I'm also going to rely on this concept of dominant balance physics. If I were to take this laser pointer and throw it across the room, and ask you to build a model for that, you'd probably say, well, it's just F equals ma. And of course, I could ask you, why did you not consider my quantum mechanical effects, or the air resistance, or the thermodynamics? They're all there, aren't they? You'd say, because well, yes, but dominant balance physics is that I threw a mass across this room at a certain velocity, and F equals ma pretty much is going to get 99.9% of it correctly. So the dynamics is clearly much more complicated, But what the manifestation is, the measurement, is just the leading order terms. So I would say that's what we're going after here. The physics is clearly much more complicated. So parsimony. This one is interesting because I think this is where we're going to have interesting challenges in machine learning. Really, are parsimony going to be, are we going to double down on that or not? At least this method sort of goes after parsimony. It's only one technique. Remember these? I'm just interested in how can you get after data and going after a problem, and how can you get some interesting ways to move forward with the problem. So here's how we're going to do this. This is just AX equal to B is math architecture. There's really nothing fancier than that. And so what is the A and the X and the B? So here it is in a diagram, a little busy, but let's walk it through. I take some data. Okay, so this is the true system, it's Lorentz. But I don't give you the system, I just give you 3 time series, X, Y, and Z. And I ask you the question, tell me what was the governing equation that produced that data? So, well, I know that it came from a system X dot equals f of X. So if I give you the data, X, you could produce X dot. By the way, that's actually harder than it sounds. If I give you noisy data, do you know how it is to do numerical differentiation on noisy data? That array is a big challenge, right? And so, often it's overlooked. I am a professional applied mathematician, and I didn't really realize until I was in my mid-40s, late 40s, how hard numerical differentiation is. I've been doing this for a long time. It's obvious, you just do these, that's so simple, why don't you think about it? Until all of a sudden I had to. And then I realized, oh, geez, this thing that we overlook when we teach people how to do numerical differentiation as freshmen or sophomore in college is actually one of the most difficult things you want to do for estimation. Okay, and given that all of our equations of motion are written as relationship among derivatives, if you don't estimate these well, you're going to be in trouble. Okay, so let's say I can estimate these well. Okay, that's the B in AX equal to B. The matrix A is a library. It is a candidate function. It's X dot equals f of X. What could f of X be? Well, go to the library. Look at your books you studied physics in. You studied lots of models. You've seen lots of different equations. You just put in all your candidate functions here. You build a library of here are the potentials. And the parsimony piece, so that's the matrix A, that's B. The X here is the coefficient that sits in terms in front of each library element. And what we know, when we go with parsimony, we say like, well, I mean, the physics is there, but really only a couple terms contribute, maybe a few terms. So which of these library elements matter? And so what I do is solve AX equals to B, promoting sparsity. And there's different ways you can do it, but when you promote sparse solutions, here are the non-zero elements, and you recover the governing equation. So that's the idea behind that. So you can go to your classic PDEs. This is what I learned in grad school. So we just simulate these. Here they are. And it's pretty nice diversity of PDEs and behaviors. But I just give you the data and ask the question, can you recover these? So this is sort of, let's say, I don't know, a validation of this method in some sense. And so the idea is you can recover governing equations, governing PDEs. And of course, this one here is interesting for us in physics, right? Because I go through the system and collecting data. Could I learn something about the dynamics of that model? Now, one of the big challenges I think overall that we have in the community is that a lot of the data we're now working with are multi-scale in nature. And multi-scale data is really hard to work with because you have micro, meso, macros level, different governing equations. And how do you connect them all together? I think that's still a big challenge for us. So this is no silver bullet. This is just at least maybe at each scale you can pull it apart and start making some progress. Okay, so this is what we did, but now let's go one step further. In that case, I just showed you, I had the right variables to work with. The fact is, we're going to come back to this issue, which is I'm taking a measurement. It's not the right variable. How do I get this structure together? And so again, here's the picture. Can I learn a latent space where I force this SINDy model? Okay. And so here's the loss function. Actually not so bad. We now have a Bayesian version of it. We have an ensemble version of this. All of them are meant to basically handle the key issue, which is I have noisy data and limited data. How do I actually do this in practice? Right? It's very easy to make perfect data and everything works. The minute you start going towards reality, you have to deal with some of these things. Okay, so we're going to do this. And so here's the example that I want to show. So here's my data. So I am at the University of Washington State School. So actually, this campus might be, I might like this design ethic. Off-white cinder block walls, off-white, the tiles that you can throw a pencil through, off-white linoleum floor. So when you drill a hole in the wall, nobody cares at all, right? There's nothing you're rooting, actually. It's like, oh, great, that was a great use of the wall. Okay, not even double as hard. Okay, but so this is our video that we want, and this is so what's coming in is pixel space. But we're pressurizing this thing to say, go find a low dimensional embedding and a latent space to represent this. And what's interesting, applying the SINDy loss in there, what it's forced to do is there's only one, so this is the model it finds, and it actually finds theta theta dot for you. It is the only variable set that allows for a parsimonious representation. So this thing, we didn't tell it anything about theta theta dot. We just said, here's a bunch of pixels. It finds this. So this is a very simple example. I understand that. But the fact is, this is where we are. And by the way, part of the reason this is so challenging is, and you can see it right here. I don't know if you can see it from far back. Do you see the shadows and the lighting? Normally, we did this for a long time. It's like, this shouldn't be this hard. But then we started to realize, wait a minute. It's actually trying to build two models. There's a pendulum there. There's also light and reflection and ray tracing. So at least we know this for this model. But when you go measure a new system that you don't know about, maybe you don't even know what shadows are in that system or whatever the equivalent of a shadow is. So it makes it really challenging to start thinking about it. So this is kind of what you can do, but it's starting to get towards technologies that you might want to go after. Let me finish with an example of using this. And by the way, that whole package is also a pip install. Pip install SINDy, ton of examples there. We're trying to put everything out there for people to use. And one of the big things that we've been working on is making them robust. The data you're going to get for real systems isn't going to be perfect data. It's going to be noisy and limited often. And so how do you use that? So here's an example of noisy limited data. So this is Ryan, and we said, okay, and this is a mouse. And in the top of this mouse, you can cut a little hatch. So you can actually view this, the brain activity as it's functioning, running on a wheel. And then as it's running on the wheel, you're actually tracking its eye motions. Okay, so here's what that might look like. We take something like this, and we actually do a time delay embedding to enrich the space in which it's embedded. And by the way, there's a whole set of math that we could think about here, which is related to what's called Tockins embeddings, okay, mathematically. But we're going to take this, and we're also going to look at the whole brain activity, and we're going to ask the question: Can we map all of everything what we're seeing down to some latent space that sort of represents the dynamics of what's going on in this mouse? And in fact, you can do this. So here, for instance, is a picture. What you're seeing on the left. Start moving. Here we go. What you're seeing on the left is the actual brain activity, whole brain activity of that mouse. What you're seeing on the right is we are building this map, encoding in and decoding out to something else. And what this is you're just watching the pupil dilations and from that reconstruct the brain activity. And that's its reconstruction after training. And you can see that it's actually getting much of the behavior correctly. Okay, the bulk behavior. This is, I think, kind of astounding in a way. So when they say the eye is the mirror to the soul, they're really just the mirror to some dynamical system in there, which is kind of happening. And what's interesting about it, you can take all of this information. Here's the picture. So I can take this iris movement, and I can map it to all of these different brain activities that are going on that they can actually measure in practice. And this is the actual low dimensional embedding space, the latent space. It's low dimensional. So all these neurons that are sitting up there, 10 millions of neurons, doing all this activity, everything's collapsing down into some kind of really low dimensional representation on some kind of trajectories. So this is kind of, I think, this is how we're starting to use these tools, right? I mean, obviously, you guys are thinking more like, you know, we're here thinking smaller, right? Like particles. We're not that far down, but this is again a model that's multi-scale. We don't typically think about what all the things we know about brain activity, but this is trying to tell us, like, actually, there's something really low dimensional here. Now, you may ask the question, we tried SINDy on this, in other words, to find the governing equations. And here's the challenge of this model. When you're doing this brain activity, imagine if I go back to the pendulum example. When we do the pendulum, we swing it, set it, it's just going. It's sort of an open loop. You're not interacting with it. You're just watching this thing. Nothing else touches it until it stops. Now with brain activity, there's all kinds of other stimulations going on, and we don't know what they are. So it's almost if I were to take the pendulum picture, and suppose I put on Harry Potter's cloak of invisibility, and then I go kick the pendulum. So you're videotaping, and all of a sudden the pendulum's like this, and it just changes direction suddenly. Like, wow, did you see that physics? Right? You would never come up with that if it was a May, because you didn't know I existed to actuate the system. So this is one of the problems here of what we're trying to do now is this next set of experiments is to have actuation signals on this mouse. Things that you do to the mouse that you know when you hit it, watch what happens. Hit it again, I mean. Hit it and let's just say generic, I show it new things. Or blow a puff of wind or play loud music, something to sort of have a signature of there was an actuation signal. Right now, this is not an open loop, it's being heavily actuated. And I think this is one of the biggest challenges we have in neuroscience. We're trying to discover physics for neuroscience, except the systems that we're always measuring are massively actuated. And so it really presents a problem. How do you, if you can't extract the actuations, you're not going to be able to actually get the governing equations out for that. I'm going to finish with a couple comments. I'll go ahead and make them. So these are some paradigms you can work through if you like. All of it's pip and stall. Here's what I'm going to say to you. Don't trust me. Fact. I've come to the very hard realization that I want to say this is don't trust anybody telling you they're doing science, any kind of machine learning that's working in science and engineering. This last year I was on sabbatical. The number of repos I cloned, I ran the code, their code. Even reran some of those examples in the paper, and it doesn't work. Right now, I think we have a real issue in the science community around this. Now, these are famous people at exceptionally famous institutions with these papers being very highly cited it just doesn't work. It's a real problem. And of course, the pressure points, it's obvious why this might happen. There's a lot at stake, funding, reputation, all the stuff that is there, right? But it's fundamentally a problem for us. And I think the biggest impact I saw was on the grad students. This is why I say this openly. Because a lot of the grad students are, oh, look, here's famous professor from famous institution, who should know better. In fact, I think they do know better, putting out there and very highly cited in a high impact journal. The student downloads and starts playing, they can't even get the code to run. Doesn't work like it's saying. Normally what they do, they don't go like that very famous professor from famous is wrong. They go like, I don't even know how to program. I feel bad about myself. And then they go into this hole of like thinking that something's wrong with them when in fact nothing's wrong with you. the other people. So I say that out loud, so just in case you're currently in like cross-validation help, you can't make a code work. But it's also something that I think we have to think about as a community, for all of us more senior people in the room. How are we going to address this? Because I think it's a real stain on us as a field right now. And so I start to make these comments, and I know they're a little bit maybe controversial. I don't mean to be controversial, but I also can't stand what's going on a little bit. And I think where we are as a community, especially when they, we saw it during COVID, trust the scientists. I'm like, I'm not trusting them. We're not even in a COVID thing where we're like, you have to be on CNN or something like this and big money, I can get the big grant. This is like just us doing machine learning on science and engineering, and we have a huge accountability issue. With that said, the AI Institute of Dynamic Systems is actually putting out a common task framework where we are building out true withheld test data sets. So we're going to start challenging people to really put things up there so that there's some accountability for this. So I'll end there. Thanks for your time.
Thanks, Nathan, and thanks for the call for
Hey, Nathan, great talk.
Thanks.
I had a question about like how you do SINDy, like basically it's a form of state system identification, right?
Yeah.
So, but in reality, when we make an experiment, we have access to Y or measurement, and
Yeah.
we don't have access to the internal state variables. So the way we do it usually is like we send excitations, and then we get the response, and then we are trying to fit a model, right? But what if we haven't driven it enough such that my measurements are not actually a true representative of my reality? Say I'm not driving it with, say for example, I don't have enough coherence between how I drive and what I see.
Yeah.
Okay, so this info is not added into the SINDy or any set of. So then what happens is I'm trying to fit a model, but what I measure is not the reality. And does it have a way to overcome this issue, which is what we usually encounter in reality?
Yeah, so there is a version of this that tries to not just fit x dot equals f of x, but x dot equals f of x plus bu. So then and of course, b can be something that you also learn. So even though if you know how you're driving it, you're not sure how it's actually hitting the system, the b would potentially take care of that. The other things that we've done in this is to say, well, if you can give it sort of impulse kicks, right? You kick it, turn off your actuator, let it sort of in some sense be open loop for a while, kick it again, but you don't do the discovery until that controller is off. So you look at these intervals of time where you're not actuating it, and you're letting things settle down. In fact, often SINDy works better by having a diversity of trajectories versus one long trajectory. So what you can put in here is not just one simulation, but multiple, lots of different initial states. And then you're trying to say, what's the model consistent with all of these? So especially if you can give it lots of different kicks, turn kick off, watch what happens, kick it again, turn it off, watch what happens, put that all into the SINDy block. That's how we're kind of handling it right now. We're pretty good with handling noise now. I always say that if you can't handle in these methods, one of the things we've worked really hard on the last few years is trying at least to get to handle 25 to 30% noise. To me, that's the starting point of even any kind of engagement with a real person. People with real data. So if you're going to come to someone in biology or engineering, like that's the baseline noise level they're going to be working on. And so if you can't hit that, what you have is a cool applied math trick, like, right, that we put over here, here's some ideas. They don't actually work in reality. Once you get to 25, 30%, you can talk about that. We've also done the ensembling tricks, which allow you to go to limited data as well. So we've worked pretty hard at trying to like get towards, can we actually go to hand this over to an engineer and it's actually useful versus, oh, you live in a math world, right? Which, by the way, I can do that. I'm in an applied math department, so I can spend my entire life working with perfect data, right? And work in the land of unicorns and fairies. But part of it is to try to get it out to people to make it useful.
Hi, this is a very good talk. So I'm curious, so when I hear people talk about like foundation models for science, this sort of thing seems like a very good use case for that. That like, if I'm developing something that, you know, is able to have a model of optics, then, you know, once it learns optics, it knows optics. I guess I was wondering if you could comment a little bit on like the ways that you can take models that are trained on, you know, large diverse data sets with large diverse, you know, different scenarios, and then potentially combine them like with this SINDy paradigm.
Yeah, in fact, that's a great question. So one of the things that's really happened, especially over the last 6 months, now, I'm sure many of you are aware of this, right? So I'm gonna call it the foundationalization of science and engineering. You take any application area. Someone there has a bunch of data there, and they're gonna build a foundation model on it. And so whether that's, so we're starting to see it in fluids, time series analysis. I mean, everybody's just building a foundation model, right? You just take one of these LLMs, transform networks, just you like, let's just put in one type of data, which is, you know, E&M data. So I think these can be very powerful tools. They're gonna be amazing if you can put things in. They're gonna be exceptional in interpolation, especially. Part of what we're trying to do with that is trying to figure out, but can you actually use any of this architecture in there to also give you back explainability, right? I mean, this is kind of nice in this sense that, right, it's trying to give you things like, oh, here's some terms that are active, like you have a diffusion term, you have dispersion, like just things that, let's say, are human understandable, that are sort of in the dominant balance of some sort, right? It doesn't solve the problem, but at least the hope is that it gives you an enrichment. The fact is, I think what's gonna happen with foundation models, they're just gonna be hard to beat. You're gonna be like, oh, I'm studying E&M now, and there's this foundation model. I might come up with some new techniques. Your first bar to cross is gonna be this foundation model, which is gonna be almost impossible. Like, it's gonna be really hard to beat it. Okay, unless you're gonna do something really different, so you're gonna really walk out of the regime and do an extrapolation, that foundation model. So I think it's gonna change science for us. I mean, to some sense, to a good point, I mean, I write code all the time now with Chad as my partner. All right? Well, ask you for a little code block, it's just so much faster and more efficient. And Chad doesn't have the annoying habit I have of putting a typo in. Right? It's amazing. I keep, if it learned on the internet, how does it not have typos everywhere? It's my code, right? I forgot the colon there, like all these little things, like, oh my gosh, that just saves just that. The savings alone in that and time and programming is massive. So I don't know. I'm excited, although I feel like we all just have to put seatbelts on and crash helmets, and there's no option. This is where we're going, and it's not clear where we're ending up. We're moving exceptionally fast. I'm kind of uncomfortable with it, but I'm just gonna go for the ride. It's like a roller coaster ride where they turn off all the lights. You don't know what's coming up. Yell if you need. But just, you're strapped in, go, right?
I have a question just to make things clear. I was not sure to understand. In the dynamic model composition.
Yeah.
Are you extracting the linear part of the dynamics, or are you finding a transformation? Are you transforming the nonlinear dynamics into a linear form version of it? Are we losing some nonlinearities, or are we keeping everything in the linear form?
A good question. So two answers to it. The first answer is, in the first version I gave you, I just said, this is a nonlinear dynamics. I will just fit the best linear model. And a lot of times it works surprisingly well. I mean, I think that's maybe part of the moral of the story is like, and you know, look, it's hard to sell people, look, I did something super fancy if they're a linear model, right? Because sometimes it doesn't like generate excitement. Because you didn't say, I built a transformer with this many layers and the convolution on the end and it does this and magic. It's like, yeah, but I beat that with a linear model, right? You can't get that to Neuros. This is part of the problem. There's a lot of unaccountability there, in my view. The second part was to actually make a transformation to make it more linear, so that the linear model is even a better approximation. In either case, you're trying to say, I am just fitting a linear model to this data. And like I said, this is the accountability sometimes has to be there that it's not, which is, I've seen many Neuros papers where you can actually beat what they did with a linear model. And it's a little bit of an embarrassment, and, you know, what we're also moving to is like, well, I can't even run their model, because they did it on 200 GPUs, I got 3, right? This isn't a problem unless I commit to working with Google or somebody who's gonna give me access to GPUs. So we're in a really interesting, landscape, I think, for this.
Take one more question before the coffee break.
So I want to ask you about the sparsity loss term in your SINDy, particularly with the super high dimensional things like
Yes.
this rat's brain model, or whatever.
Yeah.
I saw this awesome talk from Miles Cranwright,
Yeah,
who's
yeah.
one of your collaborators,
Yeah.
and he showed this incredibly compelling example of the heliocentric versus geocentric model extraction with SINDy.
Yeah.
Like, there's more terms in the epicycles model.
Yeah.
And so if you just run that through your thing, you get something, you want something simpler, you get the geocentric model. Like, oh my God, if only Ptolemy had that, like,
Yeah.
wouldn't that be incredible?
Yeah.
But with the really high dimensional things like the brain, where you don't know how much complexity might be hiding under the hood, how does the sparsity loss term, like, do you worry about it overfitting or, damping out all of the high frequency things that might actually be significant when you compact everything into a really low dimensional attractor? How can you be sure?
Yeah, no, it's a great question. I think one of the real interesting issues with any of these neural networks, and this was actually studied early on, there's a paper by, I think, who's on it, Goodfellow, Bengio, others, on basically neural network biases in training for low frequencies. So even an autoencoder like this, to hear, one of the things that happens oftentimes if you have spatial data with multi-scale, it just simply says, I'm going for RMSE. I can just blur my vision, because that's going to give me the good score. So oftentimes what happens is if you do these things, right, this spectral bias that happens in neural networks comes to play, and it acts basically like a signal processing filter. Boom, chops off high frequencies. Now, what we are working on now, though, is one thing that you can do is instead of doing this, you could in fact encode first into a compressive space like an SVD. Because when you actually do that, if you look at the SVD modes, they actually preserve high frequency features. And then you train in the compressive space. That's one option. A second option that we're playing with is you add to your loss term over here another loss term. Instead of going just after RMSE, you say, look, if I look at the power spectral density, and I look at those tails, I'm going to actually look at my data and I look at the decay rate on the tails of the spectral density. And I'm going to actually force whatever thing I learned to map me back to make sure to preserve that spectral density. So for instance, in fluid dynamics, we have these decades, hundreds of years of knowledge about what happens when you have cascade of scales. We have these -5/3, -3, power law decays on right inertial range. Build them into your loss function. Force that neural network not just to pay attention to like there's a big blob of fluid.
So that's great. That's really wonderful for the problems that are like this, where you have that kind of prior knowledge. And you can tune these lambda parameters as you need. But when you're going to like I'm not a neuroscientist, FYI.
Yeah.
But I have this assumption that it's more intricate and complex.
Yes, I believe so. But I don't think I think what we're gonna do is try stuff, and then we'll start figuring things out. But actually, I think this becomes also, right now, this is, in some sense for that, is a tool that you could say many of the things we've done have just been validation. I already knew that. I turned a neural net to do it. That model with the mouse is our first model out where we're like, we have no idea what the truth is. But we're starting to get, so in other words, this is no longer a tool for discovery, it's a tool for, in the sense of like, I've discovered the truth. This is a tool for exploration, right, in some sense. So I would frame what we've done is simply exploration. So we've got some things, we've learned something, and now we have to, okay, now can we use these types of tools again to get us further and further down the road? So eventually we can say, we discovered something. So that's an open question still.
Thanks.
Somebody, by the way, is gonna give a name to this. Right? It's not like, oh, when did we have the concept of energy, potential energy, kinetic energy, temperature? These are actually late in the game. Right? And now we just assume them to be true because first day of physics, you start learning about symmetries and conservation laws and conservation of energy, conservation of mass, momentum. All these things at some point we had no idea what they were. We gave them names. Now we call them truths. Somebody's going to figure this out. Quite a neuroscientist who can put some kind of meaning to some of this, and we'll call it something. Oh, this is the blah, and it's blah, and it'll make some kind of sense somewhere down the road. And then 100 years later, it's like, how did people not know this? This is obvious that it's conservation of mass and energy. But at least giving us clues that we have something to go after. And I think that's at least from an exploration point of view, I think it's nice to have new tools available to us.
Great, well, thanks Nathan again.